In this segment, we're going to continue our talk about entropy, and we're going to talk about how we can apply an entropy balance for a system. So we know that we have conservation equations for energy and mass, and we know that those take sort of the same form. So for energy, the change in energy contained within the system is equal to the net amount of energy transferred across the system boundary. We could do the same thing for mass, and it looks pretty much the same. We just replace that word energy with mass. So in other words, what we're saying is energy and mass are conserved. However, entropy is not. That doesn't mean we can't do an entropy balance on a system. We can. It looks just a tiny bit different. So it starts out looking the same. So we have the change in entropy stored within the system equals the net amount of entropy transferred across the system boundary. But then we have this additional term, and it's the amount of entropy produced within the system. And it was this term that Clausius was after, is a term that's indicative of how much usable work we lose for a given process. So for this term right here, we use sigma. And if sigma is 0, it means you have a completely reversible or internally reversible process. So there's no internal irreversibilities within the system, no friction or anything like that. If it's greater than 0, it means you do have irreversibilities within the system. In other words, it's a real process, because as we've said before, there's no such thing as a completely reversible process. It cannot be less than 0. That would be an impossible process. So if you calculate a sigma that's less than 0, that just tells you that the process is not possible, and maybe it can't go in that direction, it has to go in the other direction. All right, so we're going to talk in the next couple of lectures, or the next couple of segments, about specifically what those entropy balance equations look like for a closed system and for an open system. Thank you for watching.